Good. So welcome to 7th lecture of the series. Some announcements. You must have got the grades this morning, and there will be a recap session after the lecture. So please come and make questions, right? If you have any questions, right? Feedback from last time, I was apparently too fast, right? And last time material was quite technical. So yeah, apparently I didn't realize that you didn't really follow. So this time we also have a lot of technical material. So I'll try to go slow, not too slow to bore you, but I'll go slow to make sure that you all understand along the way. Let me know if you don't understand anything, right? Because most likely others will not be understanding it as well. And last time we also had the video problem, so I'll do the recording again anyways. I didn't have time for that yet, but until next week I'll make sure to record it again and put it on YouTube again. Last time we talked about feature attribution in general, evaluation, and 4 methods for doing feature attribution: input gradients, integrated gradients, Lime, and Shapley values. This time I'm going to continue on feature attribution a bit further, right, on a slightly different angle. But I want to recap the materials last time with a slightly different perspective now. Linearization perspective. Last time we kind of covered all these cases like input gradients and so on from the angle of counterfactuals. What if you change some of the features, and what's the response of the model, right, because of that. And now let me give you like these 2 diagrams here, one for model and the other one for the input space. To simplify things, I'm just going to write f, the function that we are interested in, as kind of 2 parts, the first part and second part, g and h. Let's say it's a 2-layer neural network like this. And there's a sample of interest, x, that we wish to kind of explain the model around. The reason I kind of introduced this is because I want to give more high-level kind of view on what we have done last time and how we're going to do it differently this time. Okay, so last time we kind of took the full model into account and tried to approximate it with gradient, for example, around the test point of interest. So one example of that was input gradient. And if you're using input gradient, you're basically linearizing the model of interest around the test point of interest. Okay, so let's say you're kind of making a small perturbation, delta, around this test point x. Then you can approximate the value of this function, where x is kind of constant now, and delta is kind of the variable. You can write down this function as a Taylor expansion, basically, where we have f of x, the baseline point, and then you multiply this delta variations direction with the directional gradient delta f, right? And then you have a small term that vanishes when you decrease delta sufficiently. So this is a perfect linear function, right? So and we understand what linear function is doing. It's interpretable function. So in a way, we are kind of locally approximating the function in the vicinity of the test point of interest. Now, yeah, sure.
Wait, sorry, what is the small o function?
Oh, okay. So small O of delta means when you decrease delta to 0, the rate of decrease here is smaller than linear. So it could be, for example, delta squared is little O of delta. Do you know big O notation? And so big O notation means the rate of decrease or increase is exactly the same, right? So if you divide these 2 values and move them to infinity or to 0, it kind of goes to constant. Little o means it goes to 0, basically, if you do it. So it's kind of asymptotically bounded by a linear function. So that's the typical way to kind of write down the Taylor expansion for differential function. And we also looked into integrated gradient, which is kind of generalizing the notion of kind of counterfactuals from kind of small perturbations around the input to entirely turning off the input to some baseline value. In this case, people like to use black pixels, black image as the baseline image to compare against. And they like to kind of explain the difference in function value between f of x and f of x naught by the summation of contributions from different pixels. And one way to kind of still try to make sense of it is by using the difference in pixel values between the current pixel value for I and the baseline pixel value for pixel I, and multiplying that with some directional gradient, which is integrated along the path, linear path between current value, current input, and the baseline input for pixel I. Okay, so it kind of also introduces some linearization of function in the sense that in this case, you're not kind of linearizing the function around the perturbation of the test input, but you're kind of linearizing the binary contribution of every feature of whether they are included or not. So either they are turned on or off, right, in the summation. And whenever there's a feature that's turned on, right, they're contributing this AI of f and x amount to the function value. In other words, you're just summing over all the pixel-wise contribution, and that's a linear function. And when some of the features are not present, you basically leave this term out of the summation. And in that sense, this is a linear function as well of binary variable of whether you're including this feature or not. And that's what integrated gradient is trying to do. Okay, is it clear? Lime as well is, now we kind of shift from continuous input space to discrete input space, where the features can be turned on or off. But now the test point of interest has multiple features turned on, as in the integrated gradient case. And now what Lime is interested in is still local behavior around the test point of interest. So instead of kind of entirely turning off, having the possibility to entirely turn off all the features in the test input, you basically turn off a single feature at a time, sort of, and then see the model reaction to these small perturbations of the test input in a discrete way, though. Okay, and then based on the perturbation patterns, you try to fit a linear model on top, which is having a very simple dependence on the binary feature of binary vector of whether you include each feature or not. Okay. So now xi is kind of indicating whether you include that feature or not. So it's 1 and 0 kind of binary value. So eventually this is also kind of doing a linear summation of all the factors beta I, where each beta I is kind of indicating the contribution of each kind of feature I. So it kind of looks similar to what we had before in integrated gradient. The key difference is that first of all, the input space is discrete in this case. And also in the previous case, we are kind of looking at the full kind of linear path between the current input and some baseline. But in this case, we are not kind of interested in this full path. We're just interested in kind of small perturbations on the test input and doing the linearization on top of that. And finally, for Shapley values, what we are interested in is like integrated gradient, the full path between the current input and some baseline input. In this case, the baseline input is the empty feature, like 0 feature. And now, unlike in the continuous space, there are so many pathways you can take between the current set of features and an empty set. there could be naturally many ways of kind of getting to this, right? So you basically consider all these paths when you do the computation. And the computation you do on each path is very similar to what you do in integrated gradient, which is along the path, you try to kind of take the gradient of the function towards the direction feature I. In this case, the feature I is a discrete kind of variable. So instead of kind of doing the upper, like gradient, which is an approximation of some function, you just take the difference between f of x and f of x minus I. Yes?
When you say different paths, you mean like the order when you move feature up?
Yeah, exactly. So let's say if you have features 1 to 3, you can go from 1 to 3, and then 1, 2, and then 1, and then 0, empty set. Or you can also go from 1 to 3, and then 2, 3, and then 3, and empty set. There are so many ways to go like this, right? And you're considering basically all of these. And there are some scaling factors put in front, like this complex expression. And then eventually you're just summing over all these values. I'm going to explain more in the re-recording of the previous lecture. So I'll leave it like this and then move on to the next topic. I hope that's all right. Okay. So now, what are we going to do differently now? So far, we were kind of happy with kind of the fact that, yeah, we are not explaining everything. Of course, you have to kind of give up on something if you want to explain something very complex. And the object they were giving up on was the input space. But now we kind of try to do it the other way around. We still try to explain the model on the whole input space, but now we are giving up on certain part of the model, right? So let's say G is something that's perhaps not super interpretable inside the model, and H is something that's interpretable, like a linear function. And then we just forget about all the complexities in G, and let's say if we actually focus on H part of the function, we get a reasonable kind of explanation of the whole function. Okay, so let me give you an example of this in a moment, which is class activation mapping. That's only working for CNNs. So I can give a brief overview of what convolutional neural network is, more precisely what kind of convolutional neural network we need to apply class activation mapping. Okay. So we need an architecture that looks like a fully convolutional first part of the network, which is going to give you a feature map. So there has been no flattening of the features into, so there the spatial dimension has to be kept all the way through the network basically to produce a score map. It could be like a 7x7 score map, or it could be 14x14, or even 28x28 feature map. And then you're going to do some average pulling on top, okay, which is a linear function. And the result of that will be kind of a vector, logit vector, which tells you the kind of the likelihood of every class of interest. If it's ImageNet, then that's going to be a 1,000 dimensional vector of logit values. So that's my H, actually. The part where we're doing the summation over all the feature values at each location of the feature map. If we have that, yeah, for example, like here, then we have reasonable kind of explanation of what the model is doing, right? Because eventually the model is eventually doing just a summation of all these values, and that's easy enough for humans to understand. So which kind of architecture allows this kind of computation and explanation? Let's take a look at the one of the first networks in deep learning, which is AlexNet. What I'm showing here is the layer profile of this network. So for each layer name, conv1, right, you have input and output dimensionality like this. Just forget about this middle part. It's kind of irrelevant. Yeah. So let's just focus on this input and output part. We see that, so 227 means the dimension of the spatial dimension, right? And then as you go deeper and deeper, the spatial dimension gets halved, right, at some places. When you do max pooling, all the way down to 6 by 6 feature map. The channel dimension is 256, okay? So now the question is, can you do this kind of explanation that I just described before? The answer seems to be no, because what follows afterwards is nonlinear. It's not a linear sum, right? You have FC layer followed by ReLU activation twice, right? So it's FC8 of ReLU of FC7 of ReLU and so on. So it's not linear. And it's again something that's not interpretable, so we can't do it. Okay, fair enough. What about VGG, which came after AlexNet? You go all the way down from 224 to 7 by 7 feature map, which is great. But again, what comes after is consecutive FC layers with non-linearity in between. So it's not linear again, so we don't have the possibility to explain this easily. A bit more modern architecture here is GoogleNet, which has a lot of layers in between. And then eventually comes the 7 by 7 times 1024 dimensional feature vector. Now if you take a look at what happens afterwards, you just have this average pooling layer followed by a linear layer. And actually there's no ReLU in between at all. So what's actually happening afterwards is fully linear. And that's something that we can actually understand. But again, this is not just doing spatial summation, like average pooling. So it's still, we need a little bit more work here to make it still understandable to humans easily. But I'm going to get to that point soon. Okay, now what about ResNet? It has a similar structure. You have 7 by 7 feature map, and then you do average pooling and then FC layer. So these are also linear, the same structure as GoogleNet. Okay, so given such a model like GoogleNet or ResNet, how do you produce a score map, which is going to tell you where the model is focusing on? So I'm going to give you some notations here. So F bar means the feature map, the last feature map of the convolutional neural network. Normally what you do is you do global average pooling to produce a vector without any spatial dimension, and then you're doing a matrix multiplication on top to produce a 1000 dimensional vector for the final logic values. Okay, that's what's written here. So if you want to get the score for Australian Terrier, you're gonna kind of do dot product between the average pooled feature vector with the WL, where you basically choose the ground truth class here, Australian Terrier, for of the weight matrix. Okay, so it's a vector that you're multiplying on top, and you write down W1, W2, W3 for each of the channel dimensions of the global average pooled vector. Okay, and then you're doing weighted sum of all these features to make the final prediction. If you write this down in equation, you have F bar LHW for the feature map, and then you're doing global average pooling, which is 1 over HW, and then summation over H and W. And then you're doing matrix multiplication with WYL, where you can also plug in Y, the Y hat, the ground truth Y. And then you do softmax to get the likelihood of the ground truth class. Okay, given this model, how do you get the score map, right? And these people, Zhu Bolezu, right? He came up with this idea of using the convolutional features here and the weights that comes next, and doing the weighted summation over all the feature maps at each channel, right? By the way, the weight matrix, weight vector here, and the number of channels have the same dimension, right? Because yeah, the weight matrix is kind of applied on the global average pooled vector, right? And then if you do the same kind of weighted average of the feature values as you'd have done for the global average pooled values, then you will still get some kind of feature map, which is probably going to tell you where the model is looking at to make the decision that this is Australian Terrier. So that's what CAM is doing in the original formulation. Okay. Okay, so I always feel a bit bad to kind of go through all these details here for CAM because I know much simpler formulation of CAM, which is equivalent but much simpler formulation. But I still have to kind of explain the original formulation to kind of make a connection, right? So what I'm going to do now is to make a much simpler connection, a simpler formulation of this. For this, I need to kind of make sure that we are on the same understanding that linear operations can be swapped. They are commutative. In this case, yeah, commutative with some caveats, yeah? Maybe I chose the wrong word. But what I mean here is likelihood, again, is a composition of first doing global average pooling and then matrix multiplication. But the order of computation here between matrix multiplication and global average pooling can be swapped. So you can actually first do matrix multiplication for every pixel and then do global average pooling. And it's the same operation mathematically. So what I'm going to do is I'm going to define a new notation for this matrix multiplied output of the feature map. And I give it f y h w. Now I'm using y here because the channel dimensions here exactly correspond to the class of interest. So it's going to be 1,000 dimensional tensor. If you do it this way, then you can write down the full likelihood computation for the model as just a global average pooled vector here, and then putting a softmax on top. Okay, so do you agree with all this? Okay. Right. So as I explained in the previous slide, we're doing this, right? Global average pooling and then doing softmax on top. Now, the computation of CAM in this case is exactly just taking the y-hat slice of the modified feature map. Okay, so I told you that the feature map now has 1,000 dimensions. You just take the channel dimension that correspond to the object, the class of interest, and you just take the feature map from that dimension. And then that's right away going to give you exactly the same final feature attribution as here. Okay. To convince you further, I have some more slides to explain. Yeah, again, yeah. So I also want to kind of make a remark that if you're applying a matrix multiplication for every location in the feature map, you don't call this FC layer anymore. The standard name for this is one-by-one convolution, right? So you're applying this kernel or matrix multiplication on every pixel. And that's exactly the same thing as applying a one-by-one convolution on every pixel. And in reality, when you implement this, then you should use nn dot 2D convolution, but with kernel size 1. So I'm gonna visualize everything here again. So originally you have, yeah, depending on the network, exact network, you may have 1028 or 24 or 2048, and then 7x7 feature map. And then originally you do global average pooling to make this into a 2048 dimensional vector. And then you put FC weight, which is just a matrix multiplication. And then you're going to have 1000 dimensional vector. Yeah, that's usual computation. And what CAM is doing is you take here a small row in this weight matrix corresponding to the class of interest, and then doing the multiplication of this vector with this feature map, set of feature maps, and then doing weighted average according to the weights in this vector. And that's going to give you a 7x7 feature map. Okay. But what I'm trying to say is these two operations are mathematically identical. Whether you do global average pooling first and then doing FC weights on top, or doing one-by-one convolution first with the same weights and then doing average pooling. Yeah, now it kind of makes sense intuitively as well, right? And now for CAM computation, again, what you can do is basically take the class of interest within this final feature map with 1000 channel dimensions, and that's it. Pro, simpler implementation, it actually also gives you the same accuracy, like up to some numerical error, right? And then, yeah, maybe the con is that, as you can see, you're using more memory by doing this, but this is kind of negligible, I would say. So I don't care so much about that. Yeah. Okay, so far everything is clear. Okay, so I simplified CAM computation dramatically by doing this. Because if you have to go back to the weights and take the slice of the weight matrix, that's not beautiful. Like the code gets super dirty. As you can see here, actually. I just wrote down how to do this here. I'm not sure if it's visible, but I don't like doing that. Okay, so that's CAM. And one crucial hidden assumption behind CAM is that each of the location in the feature map is actually a kind of faithful representation of what the model is looking at. So let's say when you take a look at the feature values here, then the underlying assumption is that the values here are computed based on the kind of corresponding location in the image. It also brings us back to the receptive field question. As I have told you, the receptive field of ResNet is super huge simply because there are so many layers. And actually, there's no like mathematical guarantee that computations here will mostly be focused on the corresponding pixels here. Maybe it also comes all the way from like the upper right corner of the image. So, but we still have to make some approximation and make some simplifying assumptions. So we kind of, and also in practice, we kind of see that, yeah, mostly these locations are aligned. But we have to be aware that we are making this assumption here, okay? That's what enables basically this kind of methodology. So that was for the convolutional neural network part. I know people use transformer a lot, including myself, so maybe we should also briefly touch upon some of the explanation methodologies for transformers. I'm not super convinced about any of the ideas actually here for explaining transformers. So until I get convinced myself as well, I'm gonna make this material non-examinable because I don't buy that really either. Okay, but still, I'm gonna explain how it's done basically. Of course, you can use some of the techniques that applies to any function. So these gradient-based methods, like input gradient or integrated gradients, they can be computed, of course, for any kind of function as long as it's differentiable. Lime and Shapley, they're even more general, as long as the input is more discrete and there's a well-defined notion of missing information in the features. So I would say they are model agnostic, so they can, of course, be used for transformers, and I'm happy with the application of these on such model. Okay, the question is whether we can do something like CAM for vision transformers. And this is the architecture of vision transformer. I'm going to focus on vision transformer to make parallel between CAM and transformer. But eventually, vision transformer is also very typical transformer architecture, encoder-only transformer architecture like BERT model. So you first turn an image into a sequence of tokens. For that, you have to kind of slice all the image into kind of a sequence of patches. And then these patches are kind of turned into token embeddings, right? And then for each token embedding, you're attaching also positional embedding. I'm not going to go into a lot of detail here. Also, it's kind of out of scope for the course as well. But what is important to kind of touch upon here is that there's something called class token. Some people call it CLS token. And the token embedding for that is trainable. And the role of that token is that, you know that after transform layers, all the tokens are, token positions are preserved, right? So given a sequence of n tokens, the output of a transformer and also like output of every layer in the transformer is also a n sequence of n tokens. So eventually, when you have this CLS class token, this position will be kind of preserved all the way through, and there's going to be a corresponding output for that class token. And how this is used is you're basically going to use this class token output for making the prediction. So you're going to have a simple MLP layer on top to make the class prediction. Okay, you put softmax on top and do negative log likelihood on top, and that's exactly what VIT is doing. Yeah, so to seek possibilities to apply CAM here or any other possibilities to have an explanation for a certain part of the network, let's take a look at how the self-attention layers and how each of the layers in transformer look like. So we have embedded patches as an input, right? Like the sequence of embeddings. And these are passed to some normalization like layer norm. And then you do multi-head attention on top. And there's a residual connection here. And then you do normalization. The order of normalization and MLP, this kind of ordering could be kind of different depending on the network. Anyways, and then you do MLP on top to kind of, and then do residual connection again. And this iterates multiple times, and that's transformer. Okay, so let's probably go into the self-attention module. Okay, quick survey. So how many of you know the details here? Okay, I'll go over this still to make sure that we are on the same page. So the input to a self-attention model looks like this. So you're going to have a number of tokens as basically a sequence of embeddings, where embedding size is d, dimension is d, and the number of tokens is n. And then you're going to apply a linear matrix multiplication on top 3 times, each for query, key, and value. Whatever that means, right? And then you're going to have matrices of the same length as the number of tokens for q and k. Yeah, whatever that means, right? And then you do matrix multiplication between q and k. Well, you're actually doing dot product between the row here and row here, and then that's going to be the 1 by 1, the location, the matrix at index 1, 1, right? And then do the same for all the other rows. And that's going to be your kind of attention matrix, actually. This is called attention matrix, which is kind of dictating which locations in the input sequence should be kind of considered together to make the output. And how is the output made? First of all, you do softmax on this attention matrix. Sometimes you call this attention matrix rather than QK. Yeah, I would call this attention matrix after doing softmax. And then this softmaxed attention matrix is multiplied with this value matrix, which is again made out of X. And then you do A times V, and that's going to give you the final output of the self-attention layer, Z. Okay. Some people like to kind of give analogy here, yeah, what query is doing, what key is doing, what value is doing, and so on. But I personally don't like kind of giving arbitrary names on these because there's no guarantee that the internal kind of inner workings here will exactly follow what we intuitively think they should follow. These are just containers, right? Pipelines in the neural network with all trainable parameters, so we don't actually have any control over what they should be doing and so on. But what is important is that there's some second order features that are being computed here. So you're not in convolutions, you're always kind of having, yeah, you do have multiplications, but these multiplications are between features and weights always, okay? So these are always stacks of features and then matrix multiplication on top of it, and then nonlinearity maybe, and then it continues over and over. But the key difference in transformer architecture is that you are multiplying a feature against a feature again. Q is a feature and K is a feature. And what is interesting is that you're multiplying them together. It's a multiplication, but not against the weight of trainable weight. So this way we are introducing like, if you know like kernel SVM, you can also do like nonlinear kind of lifting of the features and so on, right? So you introduce x1 squared, x1, x2, these kind of features into the feature space. And this is kind of doing that, right? You're introducing many nonlinear second order features into computation. And that seems to help expand the capacity, like modeling capacity of transformers. But what is actually pretty nice here is that the feature, the attention map here, A, has very intuitive dimensions, which is sequence length by sequence length dimension. So it kind of already tells you what are the relationship between each of the tokens in the sequence. So people like to focus on this attention matrix to make explanation on top. So I'm going to get to that later on. But let me finish the rest of the details here. So another important detail in transformer architecture is that they use multi-head attention. So yeah, you have attention like this, but you do this multiple times per layer. So when there are 9 different heads, let's say, then you do the self-attention nine times like this. So head I is attention of different weights, yeah? And you do this multiple times. And when you get the output of each of the attention, you do concatenation of all these outputs and then do MLP layer or whatever afterwards, right? And that's one, yeah, self-attention layer like this. So you do multi-head attention here and then combine all of these together afterwards. Okay, can I move on? Okay. So now the question is whether CAM will work in this case. Remember, CAM requires some kind of aggregation over the spatial features, or aggregation over the features doesn't have to be spatial. But the final computation here for transformer involves nonlinearity. And also, ideally, it would have been probably better if we were actually doing average pooling over the sequence here, because each sequence is kind of each member of the sequence is kind of I don't have the exact reference, but people also, of course, try this as well. If I remember correctly, this doesn't work as well as in convolutional neural networks. That is also kind of understandable because in transformer architecture, the mixing of the spatial location is happening much more aggressively. Because in convolutions, you're always kind of locally expanding your receptive field. But in transformers, your receptive field, so to say, is kind of expanding to the entire spatial region from layer 1. So given this aggressive kind of mixing, it's understandable that this is probably not happening. And also, yeah, people use class token, and that turns out to work slightly better than doing average pooling, at least according to some of the papers that I read. But people still try to do something here. So CAM doesn't work in general here. Then what may work, right? So some people do take a look at the attention matrix. So if you take a look at this QK transpose, or the softmax of QK transpose, it's nice n by n matrix where n is the sequence length. So that's great. And key difference from CAM is that this is showing pairwise relations rather than unary contribution. So it's just telling you which token and which token are kind of potentially linked together. And one big caveat actually that we have to keep in mind is there are so many of attention matrices in a transformer network. Yeah, so there are a number of layers times number of heads, number of attention matrices. So in practice, that could be like hundreds of them. And it's not so clear which one of them you should take a look to make the conclusion. And also they tend to kind of give contradictory results as well. So yeah, so one example here that you can see is the visualization of attention weights. So color here means head index, okay? So you can choose some of the heads here using this tool that they advertise. And if you hover over some of the tokens, you get to see like how well this is connected to the other tokens. And you can also choose the layer, right? So there are a lot of them actually, right? So that's kind of the diversity that you're going to see, right? So if you look at the weights in different layers and in different heads, you seem to get very different observations, and it's not super clear how to make a conclusion out of this. Yeah, that's the full visualization of all the attention weights. So to me, this question is still not super well answered by the research community. Yep.
So this is for a language, right?
This is for language.
So do you have anything?
Yeah. Yeah. So for vision transformers as well, there has been quite some attempts here as well. They do a lot of things, and so far I haven't found something that's super convincing to me yet along this direction. There's something that's also called attention rollout, which is kind of doing multiplication of the attention here with the preceding layer, right? Because they're all n by n matrices, and kind of by multiplying them all the way back, you're intuitively kind of tracing back the most important factors, most important pairwise relations all the way back to the inputs. So yeah, they also do this, but if you take a look at the papers, they also have this fallacy of looking at qualitative results to make the decision, like whether this is a good explanation or not. So I haven't found a good solid work here measuring faithfulness, for example. So that's an open question. Let me conclude the section for feature attribution, and that's a good timing. Case one, ideally we want to have, perfect faithfulness for the network. But then if you have perfect faithfulness, you have the original model and the model is not interpretable. And so you have to make some sacrifice, like, for example, approximating around some test input of interest. Or you have to sacrifice some part of the model and just explain a small part of the model. So I just wanted to give you kind of a general methodology of explaining something complex. There's fundamental limitation in how well you can explain something without sacrificing anything. You still have to sacrifice something to explain this to humans because human mental capacity is kind of limited. And the technologies that we have seen so far, I would say they are quite generic. Like it's kind of a general technology that could be used in many cases. At least in training data attribution, you're going to see the same pattern in that regime as well. So yeah, the goal here is to kind of convey the general methodology that's generalizable beyond just feature attribution. Yeah, so I hope you also get that at the end of this this section of the lecture. Let's get started with training data attribution. I find training data attribution quite interesting, so I'm going to explain why this is the case. When we do feature attribution, we are kind of forgetting about the other half of the model. So when a model makes a prediction on a test input, of course, the input to the system is the test input, but the other half of the input that we forget about is the training data. Because you can write the model in this way, right? A model is a function of x and theta, and now theta is a function of training data. I'm writing z for training data, where z is kind of the combination of x and y. So I use z for x and y together. So yeah, feature attribution is about kind of tracing back the output computation all the way back to individual features in the test input. And now training data attribution is doing that all the way back to training data. Well, the other possibility is to explain the parameter in between, right? But parameters are not super interpretable to humans anyway, so people don't do that too much. Okay, so training data attribution. What kind of question are we asking in training data attribution first? And then I'm going to explain why this is more interesting. What happens to the prediction if I remove certain training sample from the training data? So let's say the model is predicting the true y on the test input of interest x with some probability. So the log likelihood is going to give you 0.1312. So that's the original log likelihood of your prediction. And now if you remove certain training sample from the training data and do the training again for the model and compute the likelihood of the true answer for this particular test input, and you're going to get 0.308. So the accuracy has improved a little bit, right? So in that sense, you're kind of computing the importance of this training sample for the prediction of the current test input to be recognized as the true class. Of course, as we have seen for input gradient, the kind of change you're making here is super small, and the kind of impact that you see is also super small, right? You're just removing one sample out of millions of samples. And then you're seeing maybe just a little bit of change in your loss. Yeah, but that's kind of the starting point for our discussion. Yeah. So we want to do something like that. Why? Because we want to take an action afterwards, right? So in feature attribution, as model developer, right, you take a look at, yeah, users are giving this kind of input to the model, and yeah, I see that some features may be more important than the others. So what, right? What can I do to improve the model? And it's not super clear. But now, when you attribute the current model behavior to training data, usually model engineers have control over the training data. So they can actually do something. And in particular, the kind of simulation that we are doing here is basically removal of training samples. So if we can kind of compute this efficiently, then that means we can kind of guess what kind of training samples should be removed from the training to improve the current model behavior. So there's closer gap between what we observe in the explanation and what we can do based on this understanding. So I find this potentially more useful, but compared to the usefulness, there's much less work. So there I see a lot of potential in potential impact we can make and contribution. So let's come back to these 3 layers of abstraction for XAI. So you first start from some real world problem, right? And then based on the components of this problem, you kind of identify the component which is more well-defined and maybe quantifiable. And then 3 is typically when you do XAI, number 2, the second stage is super expensive, like having to retrain the whole model. So you come with an approximation of that, and then make sure that the approximation is precise enough and efficient. So what are some real-world problems that are related to training data attribution? Maybe the model behaves weirdly. I wish the model to be doing well on this sample, and I want to kind of fix that. Why is that happening, right? And then what we expect the TDA, training data attribution, to give me is the contributing factor to this misbehavior. And then I can basically kind of fix these training points. It can be removing that training point, or it could be reweighting this training sample, or it could be fixing the label for this sample, and so on. There can be many actions. It could also be kind of removing a single training sample, or it could be removing multiple of them, or changing multiple of them. The other question is whether we focus on a single test case or a group of cases where the model is misbehaving collectively on these cases, right? So the whole imp region, right, where the model is kind of failing. In those cases, maybe you want to add some of the samples there to make sure the model is doing well there. So there are many possibilities related to TDA. But at least for the first part of this section, we'll be focusing on a very specific case of all these possibilities, just because that's kind of the easiest setting that we can think of, not necessarily the most useful setting. And also, this is kind of the setting that most of the prior work has been performed on, right? So let's take a look at leave one out retraining task, okay? Which is what I described before, right? So you have original data set and remove one of the points and see how much impact does that have on the loss value of the current test sample. Obviously, this is way expensive, right? So having defined the task, we need the majority of work here is done on kind of doing this more efficiently in an approximate way. If you just think about doing this in a brute force way, let's say there are n training samples, and m test samples, right? Then you have to basically go over all the test samples maybe, and then for each test sample, you have to figure out what has been the most important training sample by removing each of these ones, right? And then retraining the whole system, whole model on the whole data set again. And that's going to give you n by m model retraining, and that's super, super expensive. The order of n here is like millions, and m could be maybe thousands or tens of thousands, so very expensive. So given this, evaluation is based on faithfulness of kind of approximating this right, and efficiency. I'm repeating the same slide 3 times. So that's the task. the evaluation criteria are efficiency and soundness. So how do you measure efficiency? You just measure wall clock time, for example. So you have these methods, and just measure how many seconds these methods take for each train test pair. I'm not sure if they're measuring a train test pair here. I think so, yeah. So if you do Lisa, it takes like an hour, but or 10 hours or something, right? And then now if you use something called tracking, it only takes 5 seconds. It can actually go a bit lower than that, like less than 1 second as well. So these are kind of the selling points for these approximation methods in general. Or you can also go more theoretic and kind of give you how this scales as you increase the number of training samples or test samples or the size of the model, okay? Then you give some bigger annotations of how things are. Yeah, so I think what's probably more important is the soundness evaluation, how people do it. So obviously there's a ground truth, right? Of just removing that sample and retraining the whole model. And of course, you can compare the score between what happens if you really do that, right? This huge computation versus some approximation, right? And the x-axis is exactly the approximation here, and y is the true value. And you see, sometimes it works super well. You basically follow this linear y is equal to x line, and that indicates a very good approximation. Sometimes it doesn't work. So basically what they're saying is for linear regression, it works super well. But for MLP, like simple MLP, it starts to break. So it's kind of a negative signal here, but a good example of how one could evaluate this. To measure, to give some number here, you can also come with correlation measures like Pearson or Spearman correlation, depending on whether you care also about a perfect linear fit or you just care about the preservation of ranking, yeah, of which training sample was more important than the others. Okay, so that's the evaluation. But actually, I also want to kind of introduce some of the thoughts that we had as a group, stay group, which is we were questioning whether this LOO as a target is valid. Because if you think about it, right, you've trained quite a few deep learning networks, right? And you've probably found that for every training session, you're going to see slightly different results. So if you take a look at the prediction of a model on some specific test sample, depending on the random seed, for example, or even if the random seed was equal, right, due to some unknown reasons in deep learning framework or CUDA library or whatsoever, you're going to get slightly different results in the final prediction for this test sample. So that means even if you don't do anything, like if you have the identical training set, you'll still see some randomness in the output here for a test sample. And the question is whether, yeah, and of course if you kind of relax this fixed random seed, so you can do random initialization or you can do random batching of SGD batches, then of course you're going to see a lot more fluctuation in the function learned parameter and the function output for this particular test sample. The question is whether the fluctuations and randomness that comes from all these kind of effects during deep learning training, is that actually overshadowing the impact of a single sample removal? We thought that was pretty likely actually for general deep learning training. And we tried to measure that. So we brought this framework of Bayesian deep learning, which basically means you can train multiple runs for the same data set, and you're going to have different solutions, different endpoints for the optimization. And that's kind of, people say this is deep ensemble, and then say this is Bayesian deep learning. So we kind of take that approach. And basically you treat each of the checkpoints from these different runs as kind of posterior samples of your model training. But conceptually, the point is this, right? So you're going to have different posterior over the model weights, depending on whether you use this particular training sample or not. And the hope is that you're going to have slightly different posterior because of this difference, yeah, the green and yellow here. And if you measure the loss on top of these posterior for the test sample of interest, ideally you're also going to see quite some difference. Yeah, if this sample is actually making a big difference for the model loss for this test sample. And yeah, of course, you can also take the difference between these two random variables. And the hope is that the difference here is actually significantly greater than 0 or less than 0. Yeah. If that is the case, then we kind of know that the random noise is not eclipsing the impact of removal of this training sample. So we then came up with this hypothesis testing, where the null hypothesis is that there's no impact of this training sample removal. So we model this the difference between these two loss values as t-distribution, and the null hypothesis is that the mean of this t-distribution is 0, and the alternative is, of course, is non-zero. And this is the result. So that's the average p-value of this statistical testing over multiple training test pairs. And the p-values are very large in general. There's some case where this is low. We haven't really figured out why this is the case, really. But in general, it's difficult to expect a consistent behavior of model being affected by a single point removal more than other randomness in the training procedure. So that kind of tells us that leave on out is potentially a very ill-defined target. It's a very random target that we have to optimize for. But there are some approaches which may actually go around this issue. So people have done leave many out as well, even before the paper that I talked about. So this is exactly like the remove and predict paradigm in feature attribution. So there we also kind of did the removal of each pixel on a cumulative basis. So you remove the most important and then second important as well, and then you removed gradually all the way up to every pixels in the image. Likewise here, you can also remove the training samples according to the ranking given by the approximation. And if you do that, the hope is that if you're removing the most helpful samples for this test input, meaning that as you remove them, you should see the loss increase, right? Because they have been very helpful, but now you're removing them, so it's bad and the loss will increase. You should actually expect increase in loss as you remove more helpful samples first. On the other hand, if you're removing the most, how to say, what's the word here? Contradictory, yeah, harmful samples first, then you should actually see the loss decrease quickly. So in this way, you are kind of aggregating the impact of several training samples removed. And so you should expect more stable behavior of the model. And maybe that's a better formulation of how to do evaluation here. Is that clear so far? Yep.
How did they know which samples were harmful and helpful?
Depending on the sign of it. So some methods also give you a sign indicating kind of removing this sample will increase the loss, and then they're going to give you plus sign and negative
So
otherwise.
they did leave one out of all the samples first and then you remove them?
So, right, so I didn't really talk about method yet, but the method they consider is influence functions, for example, and that gives you a sign depending on, so that's like gradient, right? Gradient is also giving you a sign whether perturbing this pixel up will give you a decrease or increase in the loss value. So you can think of gradient here. And you can either remove the most important. So in gradient, input gradient visualization, we took actually the absolute value of the input gradient, if you remember last time. So if you tag the absolute value, then you're kind of losing this information and probably, yeah, you can't do this anymore. But in this case, they're keeping the sign of this. Okay, so before jumping into the discussion of methods, I wish to kind of describe kind of a draw parallel between the feature attribution that we've done, right? Where we've seen that intrinsically interpretable models are sort of sparse linear models and decision trees and so on. What are the analog for training data attribution? Yeah. So in this case, I would say interpretable models by design are the ones that do not have any parameters in the model. You're basically drawing conclusion about this test point directly from training point without going through a parameter stage. Do you know what this is called? In statistics, what is this called? Do you know? Yeah. Yes, yeah, non-parametric. Yeah, so exactly non-parametric. I'm going to talk about some, I mean, if you take a look at non-parametric methods, they are all sharing many similarities. I'm going to talk about k-nearest neighbor and kernel regression and try to kind of show you the philosophy behind them and how they're supporting interpretability by design. Okay. So you all probably know what KNN is doing, right? K-nearest neighbor. Let's say it's a classification problem again, and you have some features like this for class A and class B, and now you have a new sample here of class question mark, and the way you determine the class for this is just by taking a look at the neighborhoods. So let's say you're taking 3 neighborhoods elements to make the decision, let's say 3. Then you have this star and triangle. So if you have the majority voting here, your prediction should be class B. When K is 7, the majority is actually class A again, so your prediction will be A. So that's what KNN is doing. There's no parameter here. There's no kind of training procedure. You just register all the points. Maybe you can do a bit of indexing to make things faster, and maybe you can call this parameter learning. But eventually what you're doing is just retrieval of similar samples and making prediction. So maybe I can talk about like 4 criteria here. Is it counterfactual? Yes, because I can imagine what happens if I remove this triangle here, right? And then this k equals to 3 prediction will be, I don't know, maybe it will be a prediction of class A. Or is it sound prediction? There's no approximation here, right? So there's nothing to be sound or faithful. So it's yes by default. Is it selective? Yeah, because now you're explaining your prediction based on a few samples, like 3 or 7, so it can be controlled. Is it efficient? Yep, there's nothing to approximate because this is already efficient. So yeah, that's the way you think about whether this is kind of satisfying all the criteria for explainability. And yeah, this is explainable. Kernel regression. how do you do kernel regression, right? So again, here you can set the number of neighbors. You can set, for example, 16. Okay, so the data points are X and Y pairs. Okay, so the dots are training samples. And the green line here is the true function. And red line here is the kernel estimation of the function, which is basically based on, so if you're asking me what's the predicted Y value for X node, then what I'm going to do is I'm going to go to 16 neighboring samples and take the average of these 16 samples. And that's going to be my prediction. So that's KNN kernel. Again, is it counterfactual? Yeah, we can easily simulate the removal of a training point here. Is it sound? Yeah, there's no approximation. Selective? Yeah, we can control the number of neighbors. Is it efficient? There's no approximation. So, I mean, this is efficient. So actually, that was for KNN kernel. I'm also going to briefly talk about Gaussian kernel as well, where the averaging is not kind of uniform averaging, but weighted averaging. So you give slightly more weights if the samples are closer to the test point. In particular, you're using this RBF kernel, the Gaussian kernel. Okay. Right. In this case, your prediction will be basically this Gaussian kernel times the observed Y value. Yeah, so it's going to be weighted average. Is it counterfactual? Yes. Sound? Yes. Selective? Yes. Efficient? Yes. So you can control also the number of supporting samples by controlling sigma. Okay, so if sigma is small, then it will be following the data more closely. As sigma gets larger, it's less following the individual samples, but the function is also getting simpler. So maybe you have to pick the right sigma to strike the right balance between bias and variance. Okay, so that was it for potentially interpretable, training data attribution interpretable models, right? And now let's take a look at an actual method for approximating training data attribution. So the goal again is to measure the gradient. Yeah. So what influence function is trying to do is to measure the gradient of the entire function that goes from training data all the way down to the model prediction for this test sample. And in the middle, there's parameter, of course, right? So the influence of training sample go through an intermediate variable, which is parameter. So we need to do some kind of chain rule here to do the gradient computation. But here, the key crux of the matter here is that this mapping is not differentiable. This mapping is not even a function, actually. So we first need to make this whole procedure a differentiable function. And then we can compute the gradients. And the question is how to also compute this more efficiently. Okay. Let's take a look at the function from the training samples to the solution, theta, the parameter that's trained out of this. So the training procedure is a non-differentiable procedure. It's not even a function because, as we have seen, even given the same data, your train model can be different every time. So, I mean, function means given the same input, you should have the same output, but this is not the case. So a solution strategy that I'm going to introduce here is we're going to make simplifying assumptions for the model to make this a deterministic function and a differentiable function. And then once this procedure, this mapping from training data to parameter is differentiable, we're going to do that through implicit function theorem, actually, which is not examinable. And then apply chain rule on top of it. Okay. So what are the simplifying assumptions here? One, they're very strong though. So the loss that we have here is a twice differentiable function and will be strictly convex with respect to theta. And this actually ensures that the solution for the minimization problem for theta gives you a deterministic solution. There's only one answer to this, right? Because it's strictly convex. And once there is a unique solution to this, the solution, theta hat, is a differentiable function afterwards with respect to the training data. Okay, so I'm going to introduce some terminologies here. Yeah, I'm getting a bit more technical here again. So again, the question is, what happens to the current model prediction for a test sample Z if one training sample Zj was left out of the training set? Okay, so I'm going to write Z for X and Y together, and Zi for training sample. So if there's an index, it's training sample. If there's no index, then it's test sample. So the test loss will be L of Z and theta. And the training loss will be ERM. You average over the observations, the likelihood over available training data. So that's going to be 1 over n, summation over I, loss of Zi and theta together for some given theta. Okay. So given this, we can further define the solutions. So we have two kinds of solutions. One is when you just use the vanilla training set. That's going to be theta hat, which is the minimizing theta for the ERM problem. And there's only going to be a single solution here. So it's a deterministic function again. Theta hat minus j will be defined as the solution when you remove Zj from the training set. That's again going to be a differentiable, deterministic function. And the quantity that we are interested in is the difference between the loss using the theta hat minus j and the loss when you're using theta hat. So that's exactly quantification of what we want to compute, right? The question is, how do you compute this more efficiently than computing them directly? So for doing that, we introduce a new notation here, which is theta, which is kind of doing an interpolation between theta hat and theta hat minus j by introducing a continuous variable epsilon in between. So what you're doing here is you have loss with every sample in the data set, plus some epsilon times loss value for Zj. Okay, so let's say epsilon is minus 1 over n, then that's exactly the summation over all the training samples minus j, Zj. Okay, and the solution for that, the minimum for this optimization problem, is exactly theta hat minus j. So theta hat epsilon j is kind of interpolation between theta hat and theta hat minus j. Okay. And the lemma here is that if you take the gradient of the solution theta hat epsilon j with respect to epsilon and take the value of this gradient at epsilon at 0, then that's exactly going to be minus Hessian inverse times the gradient of loss at theta hat for the training sample Zj. It's a complex expression, but I'll make sense of this later on in the later slide. Hessian here means the second derivative of the the function. So you first take the vector derivative of the loss with respect to all the parameters, and then you take the derivative of this vector of gradients again with respect to parameters, and that's going to give you p by p matrix of second derivatives of the loss, where p is the number of parameters of the model. Okay, so we can either take this for granted or go into details. I chose to kind of make the proof non-examinable, but still I go into details, okay? Because the derivation here is quite interesting, but I don't want to make put too much pressure on kind of having to memorize everything here. So, sketch a proof. We just write down the definitions again. So theta hat is exactly the minimizer of this ERM problem. Theta hat epsilon j is the minimization of this perturbed ERM problem. Okay. So now we use the first order condition for optimality for both cases. So theta hat is actually making the gradient of the ERM objective to be 0 at theta hat. In other words, when you take the gradient here for the loss, and if you evaluate the gradient at theta hat, that's going to be 0. Likewise, if you take the gradient of the second objective with epsilon inside, and that's going to be like this, right? And if you plug in theta hat epsilon j, that's also going to give you 0 gradient. Okay. So now we have equations 1 and 2, which is going to be like a building block for the rest of the derivation. So we just keep that in mind. Okay. Now another ingredient is implicit function theorem, which is right away going to tell you that this epsilon theta hat epsilon j is actually a differentiable function with respect to epsilon at epsilon equals to 0. And implicit function theorem is telling you that you can write this down as a Taylor expansion again. So you have theta hat plus epsilon times the directional derivative, partial derivative of theta hat epsilon j at epsilon. Oh, this is not implicit function theorem, by the way. This is just the corollary of implicit function theorem. Sorry. Because it's differentiable, you can write it this way. Yeah. And then you have this term here plus some little of epsilon term, which vanishes when you decrease epsilon to 0. So that's the third ingredient that we keep in mind. Now, what we care about is to compute the gradient here for L at theta hat epsilon j in terms of gradient of L at theta hat. Why? We'll kind of see that. Okay, so let's just do the rest of the derivation here. So we can use the Taylor expansion that we've seen before in ingredient 3. So we just plug in the Taylor expansion of theta hat here, and that's going to be theta hat plus epsilon times the gradient. Okay, and some small term. And now we know that L is a differentiable function, which means we can actually take out this small term that vanishes in the order of epsilon, right, outside the function, and linearize it. So we will have the first term, which is exactly the evaluation of the gradient of L at theta hat. And then you're going to have a second term, which is given by the Taylor expansion again for gradient of L. We've assumed that L is twice differentiable, so we can do this. We can take this for granted that delta of L is again a differentiable function. So we can do Taylor expansion. So we have this term times the gradient of this evaluated at theta hat. Okay, so if you kind of organize all of this into a single term, you're going to have epsilon times the double derivative of L evaluated at theta hat times the derivative of theta hat epsilon derived by epsilon at epsilon 0. Okay, that's exactly the term here. Okay, and some small term that follows. So now we have this is equal to this. Okay, and then we basically plug in everything like ingredient 1 and 2 inside, and many things cancel out eventually. So first of all, yeah, we plug the expression that we just got into ingredient 2, which basically says if you evaluate the gradient of the modified objective at theta hat epsilon, then you're going to have 0, right? That's the equation. But now we are plugging in this part in, and that's going to give you this formulation here. I'm not going to read it, yeah? We have some formulation here. Now the first term cancels out. This one here is actually 0 because of ingredient 1. Yeah, that's the gradient at the optimal point, so just goes away. And then we are left with this term here. And so, yeah, so this term cancels out, so it goes away. And then we can rewrite the rest of the terms as epsilon times, remember this is Haitian, so we can just write Haitian here, times the derivative of theta hat with respect to epsilon, plus some epsilon times this term, yeah. And then that is close to 0. I'm writing close to 0 here because there's a small term that vanishes with epsilon, so this is close to 0. And if you swap things around, you can write down that if you derive theta hat against epsilon and evaluate at epsilon 0, then you're going to have minus Hessian inverse times a vector of gradients. And that was exactly the lemma that we were supposed to prove. So we have this. Yeah, it's actually not supposed to be equality. No, this is, yeah, no, this is fine because we are using evaluating at epsilon 0. Okay. So we proved it somehow. Why is that lemma important? Because eventually we want to compute this quantity here, which is the difference in loss value, when you included the training sample or when you excluded the training sample. And the difference here is actually approximated with some gradient because this 1/n is such a small value that you can approximate this with Taylor expansion again, Taylor approximation again. Yeah, so you can write this down as the difference between L of Z theta hat epsilon j evaluated at epsilon 1/n, minus 1/n, and epsilon at 0. And the difference here, yeah, you're basically making this into kind of right format for kind of approximating with gradient, right? And then if you approximate this quantity here with gradient, then you're going to have derivative of L with respect to epsilon evaluated at epsilon 0. And there's a term that comes outside, which is 1/n or minus 1/n. And so now you can express this quantity of interest that we set out to kind of approximate in terms of this gradient of L against epsilon, which we just computed in the lemma before. So plugging everything in, we define influence function as the, so we are now defining influence function as this derivative here that we are interested in. So instead of directly kind of computing this difference here, we just realize that the quantity of interest here is actually exactly this value here, yeah? And the quantity of interest here is only a scalar multiple of this so-called influence function that we are defining. So we just care about this value here, and we define that as influence function, which is kind of telling you the derivative of the whole procedure of training model and doing the inference on a test sample. And by using chain rule, you can further kind of further expand this using the lemma before and the chain rule, yeah. And then eventually that's going to give you, because, yeah, you first derive this. So instead of deriving everything with respect to epsilon entirely, you first derive this with respect to theta, and then you're deriving theta with respect to epsilon. That's what's happening here. And then if you plug in the value here, then that's going to give you, okay, I'm going to read this now. So minus gradient of L with respect to theta evaluated at solution theta hat transposed times inverse of Hessian times the gradient, the parameter gradient of loss at training sample Zj. That's exactly the formulation of influence function. And that's quite interesting and interesting to look at. So I'm going to make sense of influence function next time, okay? And next time I'm also going to talk about how to how efficient this is, right? So this is still quite inefficient. So there has to be even more approximations of influence functions to make this practical, actually. I'm going to go over all possible ways of doing that and different alternatives of doing this influence computation.